We are finally on our last section of Chapter 9, which is our Section 9.5, Solving Trigonometric Equations. Our objectives in this section are being able to solve equations involving a single trigonometric function, being able to solve trig equations using inverse trig functions and a calculator. So make sure I have my calculator on me. And then our last one is solving trig equations that are in that quadratic format. So first, let's define our trigonometric equations. And so trigonometric equations are equations involving trig functions of unknown angles. Maybe I'll use pink here. And we have two types of trig equations. We have our trig identities, and then we have our conditional equations. And again, identities are always known to be true, whereas conditional equations, they're only true for particular values of our unknown angles. For example, our theta, beta, x, so on and so forth. And so lastly, in order to solve a trig equation, we need to find all the values that make the equation true. So sometimes we'll have one solution, sometimes we'll have two solutions, and sometimes if there are no bounds, we can have an infinite number of solutions, but we need to be specific with that infinite number along our circle. And so what do I mean by that? Think coterminal angles. If there are no bounds, and let's say your solution is 45 degrees, well, it's 45 degrees, but it's also what's 360 plus 45? 405 degrees. So it's 45 plus 360 degree intervals. And that's in terms of degrees, but you can also think about it in terms of radians, and you have that plus or minus 2 pi multiples going on with pi over 4. So let's start off with our first example, where we're just figuring out is this particular value a solution of the equation that they give us? And so the equation here is our 2 sine theta minus 1 equals 0. And we want to determine first, is pi over 4 a solution? So what do we do here? All we have to do is plug it in and see if it works. We're going to let theta be equal to pi over 4. And so 2 sine of pi over 4 minus 1, is this indeed equal to 0? Well, what is sine pi over 4? That's simply square root of 2 over 2. Multiply this by 2. Again, remember 2 as a fraction is 2 over 1, so these 2's will cancel out to be 1, so we're left with square root of 2. And then we can't forget about that minus 1. And is that true? Is the square root of 2 minus 1 0? No. The square root of 2 and 1 are not identical. Therefore, pi over 4 is not a solution. Now, the second part of this example is asking us, is pi over 6 a solution? So we're going to tackle the same steps. It's just now our theta is no longer pi over 4, it's pi over 6. 2 sine pi over 6 minus 1, is this equal to 0? And sine pi over 6, that's the same as just sine of 30, which is simply 1/2. 2 times 1/2, and I should properly write this out. I'll use a different color so you guys can distinctly see that I'm substituting in 1/2 for pi over 6. And so 2 times 1/2 is just 1. And so 1 minus 1, does that give you 0? It does, which means pi over 6 is indeed a solution. And we're done. Okay, let's continue. So solving trigonometric equations. We often start by just isolating the trig function, just like we do in normal algebra, and then we find the solutions within that given interval, or if there is no interval or no bounds involved, then we just want to find all those possible solutions. And so there's one thing to keep in mind. When we're dealing with trig functions, we're dealing with periodic functions, meaning their values repeat. Think of the unit circle. Goes on forever and ever and ever. So for example, when we're looking at our sine and our cosine, they're repeating every 2 pi. And what does that mean? That means if theta is a solution, then every theta plus 2 pi k, where k represents any interval, and it's not just pi plus 2 pi k, it's also pi minus 2 pi k, is a solution as well, aka our coterminal angles in radian format. If you wanted to look at your coterminal angles in degree format, you would change that 2 pi to just 360. So it would be theta plus or minus 360k, where k is any integer. And so this pattern applies to other trig functions as well. You just want to figure out what is the period of the function. So when you're dealing with tangent functions, our period is no longer 2 pi, it repeats every pi. So it would be theta plus or minus pi k, where k is any integer when we're referring to our radians. And another thing to keep in mind, and we'll really realize this during the section, is the fact that trig identities can really make the process much easier when we are trying to solve these trig equations. The last note that I want to make on this page is unless the domain of the variable is restricted to an interval, we need to find all the solutions of the trig equation, aka we need to have this format. And to do this, we first find the solutions over the interval whose length equals the period of the function. And then we add the multiples of that period to the solutions found. And so that's where, again, our unit circle really helps us out from a visual standpoint, and then using our knowledge of the quadrants and where our trig functions are positive versus negative, depending on what quadrant we're in. So this brings us to our example 2, where we're asked to solve this equation. Cosine theta is equal to 1/2. And we want to give a general formula for all the solutions. And then we want to list 8 of the solutions. Okay. So we have our cosine theta equals 1/2. And so let's look at the period. Our period is simply 2 pi over our absolute value of b. Our b here is equal to 1. And so we get 2 pi over absolute value of 1 is just 1, which gives us 2 pi. So we are going to look at our interval from 0 to 2 pi. And I'm going to draw out our unit circle off to the side here so that, again, we just have that visual image of, okay, if we're looking for positive 1/2 and we're dealing with the cosine function, then we're really highlighting all of our solutions in both our first quadrant, because everything's positive in our first, and our third quadrant, because all cosine related functions are also positive in that fourth quadrant. And so now we ask ourselves, cosine of what angle gives us 1/2? And this is one of our famous angles. We know sine of 30 is 1/2. So cosine of 60 degrees is 1/2. So when we plot this out, this is one example of our terminal side giving us that 60 degrees, which in radians is just known as pi over 3. And so in that fourth quadrant, we're looking at a negative pi over 3, or if we know that a full revolution is 2 pi, also known as 6 pi over 3, and we subtract a pi over 3, we end up with 5 pi over 3 to be represented here. Okay. And we pretty much solved it along our interval from 0 to 2 pi, but remember that first question is asking us to give a general formula for all solutions possible. So we want to incorporate all of our coterminal angles now. And so we can state, okay, our theta is equal to pi over 3 and 5 pi over 3 multiples, which if you guys have a mind for degrees, again, this is the same as 60 degrees and 360 degrees. But how do we represent the general solution for all of this? We can just state, okay, well, pi is equal to pi over 3 plus or minus our 2 pi k, where k represents any integer. And remember, integers are any positive or negative whole numbers and 0. But then we also want to state that our angle theta could be 5 pi over 3. And then we want to represent all those coterminal angles. So we have our plus or minus 2 pi k, where k is an element of all of our integers. Okay. And that's it. This is our general formula for all of our solutions in radian format. Now, if you wanted to do it in degree format, let me just write general formula for all solutions. If you wanted to do it in degree format, then you would just look at, okay, 60 degrees plus or minus 360 k, where k is an element of all integers, or the 360 degrees. I made a mistake here. 360 minus 60 gives you 300. So it's 60 degrees and 300. So 300 plus or minus 360k, where k is an element of all integers. And I'll include that right below this one. Maybe I'll shrink this to make it a little more organized for you guys. So I did the liberty of putting the degrees down here if you guys are um, more comfortable with that conversion. But we didn't finish solving this problem because the second part is asking to list 8 of the solutions. So essentially what we just have to do is let's pick another 3 coterminal angles for pi over 3, and we can list them out, and then another 3 coterminal angles for 5 pi over 3, list them out, and then we have our 8 solutions. And then I'll do the same for another 3 coterminal angles to 60 degrees, and then 360 degrees. What I'll do is I'll just add multiples of 2 pi or 360 in each case. But again, you can also subtract 2 pi multiples. I just prefer positive numbers. All right, so let me do that for you guys. And there we have our 8 possible solutions in radians and our 8 possible solutions in degrees. Obviously, there are an infinite number. I just chose 8 ones. So depending on how you guys solved this problem, you might have different possible solutions in your result. Let's move on. Our next example, we're asked to solve this equation, and now we're given bounds, which makes our life a little easier because now we only have a particular number of solutions. Anytime we have bounds, that's a good thing. That means, okay, we have a definite number of solutions within that interval. Let's just find them all, and then we're done. So let's write out our equation. We have 2 sine theta plus square root of 3 is equal to 0. And moving forward, I'm going to put my final solutions in the format that they give us based off of the intervals that they give. So because it's in radians, I'm only going to give my solutions in radians. Every now and then, I might put in degrees to just help you guys visualize it a bit more. But for the most part, I'll just keep it in radians if, again, our bounds are in that format. So we want to solve for theta. I'm going to go ahead and subtract square root of 3 from both sides. And so now we're looking at 2 sine theta is equal to negative square root of 3. And then I'm going to divide both sides by 2. And so now we have our sine theta is equal to negative square root of 3 over 2. Now I'm going to, off to this right-hand side here, I'm going to put in a nice little visual. So we have our coordinate plane. And again, let's put in our acronym, All Students Take Calculus, which really tells us, okay, which quadrants are our sine-related functions negative, right? Because our solutions here have to end up being negative. So it's not the first and second quadrant. We're looking solely at our third and our fourth quadrants. And now we ask ourselves, okay, sine of what angle? Well, sine of what angle gives us square root of 3 over 2. And these are intervals of pi over 3. But again, pi over 3 is in that first quadrant, so we need to look for our reference angles to that. So we have our pi over 3, I would say is about there, which tells us that in our third and fourth quadrant, if that's pi over 3, and then we have another pi over 3 here, then what are these terminal sides? Well, pi, also known as 3 pi over 3, plus another pi over 3 will give us 4 pi over 3. And then we have 2 pi, also known as 6 pi over 3, minus a pi over 3 gives us 5 pi over 3. And we got our solutions now because again, we're just looking at our interval from 0 all the way to 2 pi. So we only have two solutions, 4 pi over 3 and 5 pi over 3, which from a degrees standpoint is just 240 and 300 degrees. And so let's fill that out. And we're done. Put in our radians there. Cool. Example 4. So lucky for us, once again, we have an interval that we're looking at. So we're going to have a definite number of solutions. In this particular problem, we are given 2 sine squared theta minus 1 is equal to 0, which is, I believe, one of our double angle formulas. No, it's close. This is our, if it was 1 minus 2 sine squared theta, it's really bad handwriting, then it would be our double angle of cosine. We don't need that for this problem though. Okay, inverse operations. We get 2 sine squared theta is equal to 1. Let's go ahead and divide both sides by 2. So we're looking at our sine squared theta equals 1/2. Now let's go ahead and take the square root of both sides. So we have our sine theta is equal to plus or minus 1 over our square root of 2, rationalize the denominator, and we're looking at plus or minus square root of 2 over 2, which makes a huge difference because now we have no restrictions on the positive or negative signs. Now all 4 quadrants is free game, meaning we are going to end up having 4 potential solutions for this problem. And so now you want to ask yourself, okay, sine of what angle gives you square root of 2 over 2? And this is simply pi over 4. So now let's plot in our reference angles for pi over 4. And when we do, we have, okay, pi over 4 here. And then pi minus pi over 4 is 3 pi over 4. Pi plus pi over 4 gives you 5 pi over 4. And then 2 pi minus pi over 4 is 7 pi over 4. And so these are all of our solutions in radians. Theta is equal to pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. And I'll put in the respective degrees right below. And so these are the respective degrees related to the radians. And we are. Why do you want to go out so shame? So now let's move on to our example 5. So with this example 5, we are asked to solve this cofunction identity. Tan of theta minus pi over 2 is equal to 1. And once again, yes, we're given bounds, so we have definite solutions here. What do we know about tangent? That's just sine over cosine. So why don't we rewrite our tangent of theta minus pi over 2 to be sine of theta minus pi over 2? divided by our cosine of theta minus pi over 2. And then because we're looking at cofunction identities, think about our triangle sum theorem, knowing that the three angles in every triangle add up to 180 degrees. And so sine of theta minus pi over 2 is the same as just cosine of theta. And our cosine of theta minus pi over 2 is the same as just sine of theta. Uh, there's a slight correction I do need to make. Cofunction identities starts with our pi over 2. So we actually need to factor out a negative. So I'm going to, why don't we move this off to the side for a moment? And I'll put this in a different color so you could really see it. Let's factor out a negative from each of these parentheses. And when we do, we end up with sine of our negative in parentheses positive pi over 2 minus theta. And so now it's in our cofunction identity form. All divided by cosine, pull out that negative, pi over 2 minus theta. And what do we know about sine functions? Sine functions are odd, so we can pull out that negative altogether. And even functions are, or cosine functions are even, so we can actually just cancel out that negative. And so we end up getting negative sine of pi over 2 minus theta, all divided by just regular cosine of pi over 2 minus theta. And sine of pi over 2 minus theta is the same as cosine of theta, but we need to stick that negative in front. So we have negative cosine of theta. And then cosine of pi over 2 minus theta is the same as our sine theta. So we just were missing that negative. Let me clean this all up and just move everything onto one row. Okay, that was the hardest part. Now our life is a little easier because now we have our negative cosine of theta all over sine theta set equal to 1. 1 as a fraction is just 1 over 1. So when we cross multiply this, we end up getting negative cosine of theta is equal to sine of theta. And so what does this mean? We want to figure out, okay, let's draw out our little circle off to the right. What values of theta make it so our sine and cosine are equal, but keep in mind our cosine is going to be negative, whereas our sine value itself is going to be of negative sign, but how do I put this? We just have to be mindful of what quadrant we're looking at when it comes to the relationship between our cosine and our sine, aka we're not dealing with our first quadrant straight off the bat, because if we do, then this value is going to end up being positive, and then this value is positive, but multiplied by a negative will give you a negative value. So let's just exclude that first quadrant. We know the only value of theta, which would make cosine and sine equal to each other, is our famous pi over 4, aka 45 degrees. So what we can do is, why don't we draw those reference angles in for our second, third, and fourth quadrant. And when we do, we get our 3 pi over 4 our 5 pi over 4, and our 7 pi over 4. All students take calculus. And then again, we want to ask ourselves, okay, left side negative, right side positive, but they both need to end up equaling each other. So if we chose this 3 pi over 4, this would remain positive, but then if we plugged it in for our cosine, we would get negative square root of 2 over 2. And then we multiply that by a negative, and we once again get positive. So we know that 3 pi over 4 is indeed a solution. So we're going to make that green. All right, let's try for our tangent. If we plug in sine of 5 pi over 4, we get a negative square root of 2 over 2. But if we plug in cosine, we get a negative square root of 2 over 2. However, if we multiply that by a negative, that becomes positive. So this is not a solution. And then last but not least, let's try the 7 pi over 4. We plug that in and we get positive square root of 2 over 2 times a negative gives us negative square root of 2 over 2. And sine of 7 pi over 4, once again, gives us a negative square root of 2 over 2. So we have another solution. And because we're looking at solutions between 0 and 2 pi, these are our only solutions. So our only solutions are 3 pi, all right, are theta equals 3 pi over 4 and 7 pi over 4. And then I'll also maybe write in, we were looking for multiples of that square root of 2 over 2. Some variation of that, including negatives or not. And that's it. So let's keep going and move on to our example 6, which again, we once again have an interval that we're looking at, so we have a definite answer here. We're asked to solve the equation secant squared theta minus 2 is equal to 0. Let's utilize our inverse operations. And so we end up with secant squared theta equals 2. Let's take the square root of both sides. And so we have secant of theta is equal to square root of 2. Secant is the same as 1 over cosine of theta. Square root of 2 is the same as square root of 2 over 1. Let's go ahead and cross multiply. We'll zoom in. So we're looking at square root of 2 cosine theta equals 1, which just means cosine of theta is equal to 1 over square root of 2. Rationalize the denominator, and we're looking at square root of 2 over 2. Once again, 45-degree variations, aka pi over 4. Draw out our unit circle to the side here, put in our acronyms. We're looking at values where this is positive. So we're going to highlight our first quadrant and then our fourth because it's cosine related functions that are positive. And then we'll put in our terminal sides at those 45 degree, those 5 pi or 4 pi 4 pi. The pi over 4 multiples. So we have a pi over 4 here. And then we have a 7 pi over 4 here. And, ooh, I made a mistake, right? Because when we take the square root, we need to account for the positive and the negative. Which means all quadrants are included. So let's go ahead and highlight everything. Draw in those additional terminal sides. That's why it's always good to check over your work. And so we also have 3 pi over 4 and 5 pi over 4. And that's it, because we're looking at the intervals from 0 to 2 pi. So all of our solutions, therefore, theta is equal to pi over 4, 3 pi over 4, 5 pi over 4, and our 7 pi over 4. And we're done. So now let's move on to our second objective for this section, which is being able to solve trigonometric equations using a calculator. And so not all trig equations can be solved exactly, which is something to be mindful of. And so we want to, in those cases where we can't utilize our unit circle and our special angles, we need to really rely on the use of our calculator and those inverse functions on our calculator. So we use a calculator. Let me put this in orange to find our approximate solutions. So now let's take a look at example 7. Where that first one, we still don't have to use a calculator here, but that second one, we are going to have to use it. So with our first, we're looking at the intervals from now negative 2 pi to 2 pi. And so we have sine of theta is equal to 1/2. Which means our theta are our multiples of pi over 6, also known as 30 degrees. So pi over 6. And because it's positive 1/2, we're only going to look at our first and our second quadrant. So we also have our 5 pi over 6 in terms of radians, aka 150 degrees. But it's along that interval of negative 2 pi to 2 pi. So we want to think of, okay, now let's add in an additional 2 pi to each one of these. And when we do, what do we get? It's from negative 2 pi to 2 pi. So we're actually not adding that interval of 2 pi, we're subtracting. And so pi over 6 minus 2 pi gives you that negative 7 pi over 6, also known as negative 210 degrees. And then we want to look at 5 pi over 6 minus 2 pi gives you, I think I switched them up. Pi over 6 minus 2 pi gives you that negative, I'm just going to do the math. I can't think right now. Yeah, it's negative 11. negative 11 pi over 6. And then if we did the 5 pi over 6 minus our 12 pi over 6, then we get what I said before, our negative 7 pi over 6. So respectively, negative 210 degrees and negative 330 from the degree format. And so there we have it, our solutions of theta from our negative 2 pi to pi. And then, oh, they did ask us to put in the general formula as well. So with the general formula, when we are given no interval, we just take our two solutions over that 2 pi revolution, and then we want to add or subtract our multiples of 2 pi to that, or 360, depending on if we're in radians or degrees. So I'll put that in right below over here. So I just put the general formula for radians, but again, if you wanted to do it in degrees and they asked you to specifically do it in degrees, then it would just be 30 degrees plus or minus 360K, where K is an element of our integers. All right, that completes our part A for this problem. Now let's take a look at our part B, where we do need to utilize a calculator now because we're not dealing with some famous angles here. And so we're given cosine of theta is equal to 0.4, which you can keep it as decimal form, or you could change it up into cosine of theta is equal to 2/5 if you like fractions more. And now we're going to utilize our inverse function of cosine inverse. We're going to apply that to both sides. And when we do, left-hand side now becomes theta, and our right-hand side is cosine inverse 2/5. So when we calculate this out, I'm going to keep it in terms of degrees, just for simplicity purposes. I think when it's in radians and it's in decimal format, it might be a little confusing for some students. And so we have, once we plug this into our calculator, we end up getting, I believe, yeah. So it's 66.42 degrees. And then it's the same exact procedure. We're looking at the positive version of this, and it's cosine. So we're highlighting that first and that fourth quadrant. And then we want to figure out what are our solutions from negative 2 pi to 2 pi, and then what is our general formula. So our general formula, we're looking at 66.42, and then in our fourth quadrant, it's just 360 minus that, which gives us 293.53 or 58 degrees. So 293.58 degrees. And then so our general formula is going to end up looking like the following. We have this plus or minus our 360K, where K is an element of our integers. So 66.42 degrees plus or minus 360 degrees K. And then we get 293.58 degrees plus or minus 360 degrees K, where K is an element of our integers. And then last but not least, let's solve all of the solutions from negative 2 pi to pi. And so when we do that, we get the following. Our theta is equal to, if we do 0 minus the 66.42, we get the negative 66.42. And then if we do our 293.58 degrees, that is, oh, that corresponds with the negative 66.42. And then the 66.42 degrees corresponds with negative 293.58 degrees. So we just end up with our negative 293.58. I'm putting it in increasing order, comma, negative 66.42, comma, 66.42, and then comma, 293.58 degrees. And that is it. So now we have it, and we are finally moving on to our third objective for this section, which is solving trig equations in a quadratic form. And so we know that many trig equations can be solved using techniques that we've already know and learned before. But now these next examples are really going to focus in on using our quadratic formula and solving or factoring from there. Okay. So we're asked to solve example 8, 2 sine squared theta minus 3 sine theta plus 1 is equal to 0. And so first, straight off the bat, we are going to let our sine theta be equal to x, so that wherever we see a sine theta in our equation, we can replace it with x, and now we're back to our good old quadratic formula. 2x squared minus 3x plus 1. And so let's see if we can factor this. Let's try and utilize our AC method here. So A and C, 2 and 3, what are factor pairs, of 2 and 1 that add up to negative 3. And so we simply get negative 2 and negative 1. So we can break this up into keep that first and that last term the same. And we manipulate those middle terms with our minus 2x minus 1x. So now we can use our factoring skills, and we'll factor out a 2x from those first two terms. And then we'll factor out just a 1. Now let's do a minus 1 from those last two terms. And if we did this correctly, inside our parentheses should be exactly the same, so that we can factor that out. We'll factor out that x minus 1, and then we're left with 2x minus 1 in that other parentheses. And so now that it's in a beautiful factored form, we can solve for our values of x. We have x is equal to, if you set 2x minus 1 equal to 0, then 2x equals 1 and x is equal to 1/2. And then set x minus 1 equal to 0, and then you get x is equal to 1. So these are our two potential solutions, but we want to now utilize this and plug back in our x for sine theta. So we have sine theta is equal to 1/2. And then we have sine theta is equal to 1. And we want to figure out what are all of our solutions where this is satisfied. Okay. It's both positive, so we're just looking at our first and second quadrants when we're dealing with our sine. Sine of 1/2 is pi over 6, aka 30 degrees. So we're looking at pi over 6, and we're looking at 5 pi over 6. And then for 1, the only one in our first and second quadrant where that makes it true is along our y-axis, aka sine of pi over 2. Therefore, we got our 3 solutions. Our theta between our bounds 0 to 2 pi is simply pi over 6, pi over 2, and 5 pi over 6, also known as 30 degrees, 90 degrees, and 150 degrees. And there we have it. That completes our example 8. Let's do example 9 together, which we have our equation to be 5 sine theta cosine theta plus 4 cosine theta equals 0. And so if we want to use our factoring skills, we can factor out a cosine theta from each term. And we're left with cosine theta in parentheses 5 sine theta plus 4 is equal to 0, which means we set cosine theta equal to 0 for some potential solutions. And then we set our 5 sine theta plus 4 equal to 0. So we're going to have to use a calculator for that side. Which means if we end up subtracting 4 and then dividing both sides by 5, we're looking at our sine of theta is equal to -4/5. So utilizing our knowledge of our inverse sines here. And again, I'm going to keep this in terms of degrees. We're looking at negative sine values here, so third and fourth quadrants only. And so, let's see, -0.8. We get -53.13, and then we want to figure out the respective of that, and that's our -26.87 in our third quadrant. Yeah, that makes sense. Okay, so our theta is equal to -53.13 degrees and -126 point, I'm going to say about 87 degrees. And then if you wanted to look at it as that general formula, because they're not giving us any bounds here, so we want to include our coterminal angles, we can also view these negative values as positive if we go in our counterclockwise direction. And when we do that, we're looking at 233.13 degrees. So I'll write or, and I'll put in the multiples. Theta is equal to about 233.13 degrees plus or minus our 300 and 60 k, where our k is an element of our integers, or 306.87 degrees, plus or minus our 360k. Or again, our k, I'll put this for both of them, is an element of our integers. I sort of solved the harder one first. I shouldn't say it's harder, it's just a lot weirder numbers we're dealing with. But that makes now that left-hand column a little bit easier. What are our values of cosine? So cosine of 0 is going to be at our 90 degrees and at our 3 pi over 2 on our y-axis. So pi over 2 and 3 pi over 2. And we just want the general form of that. So we just have pi over 2 plus or minus 2 pi k. So plus or minus 2 pi k and 3 pi over 2 plus or minus 2 pi k, where k is an element of our integers. And that's it. That completes this example. See if I can box this out, maybe move it over a little bit. Or shrink it and then box it. I believe we have one more problem from this section and then we're done.